All right, one of the last things we deal with when we talk about intermolecular forces is the phase change part of it. Being aware of what the terminology is for the phase changes and whether it requires to add energy or remove energy. So we talked about a little bit about this during the thermodynamics chapter or thermochemistry chapter. There are 3 phase changes we talk about in chemistry. Or actually, there's a total of 6. Basically, you're going from a solid. You start here as a solid. If you go from to a liquid to a gas. If you go from a solid to a liquid, we call that melting. All of these going this direction using the SLG are always going to be endothermic, means you have to add energy. So a solid, all the particles are fixed. You add some kinetic energy to it. They melt. They turn into a liquid. If you add more kinetic energy to it, you're vaporizing. You turn it into a gas. All of these are endothermic. The one thing that does come up sometimes, especially in AP chemistry, sublimation is going directly from a solid to a gas. For example, dry ice is carbon dioxide as a solid. It turns into a gas without ever reaching the liquid state. When we talk about removing energy or allowing energy to escape the system, so from a gas to a liquid, that's condensation. From a liquid to a solid, that's going to be freezing. And then finally, deposition is the term for going directly from a gas to a solid. Those are going to be all exothermic because what that requires is a loss of kinetic energy out of the system. So kinetic energy is exiting, hence exothermic. So you definitely need to classify those as being endo or exothermic. That's the first thing. Now, heats of vaporization and fusion. Fusion is a fancy word in chemistry used for melting, and heats of vaporization is obviously going from a liquid to a gas. So when we talk about fusion, we're going from a solid to a liquid. Vaporization is a liquid to a gas. Now, the first thing that jumps out at you when you look at this graph is the heat of fusion is always lower than the heat of vaporization for any compound. Why is that? Well, to take something from a solid to a liquid, you're just basically loosening the particles up, but they're still relatively close together. So the energy requirement for that isn't very large compared to the amount of energy when you vaporize something. You're basically taking a liquid, the molecules are semi-close together. When you turn them into a gas, they're very far apart. That requires a large amount of energy, hence the orange bar on the graph is the heat of vaporization. Heat of vaporization will always be higher than heat of fusion, sometimes a lot higher because it takes more energy to move particles great distances from each other versus breaking a solid into a liquid. So you have to keep that into account. Energy changes, when we talk about phase changes, the one thing that students don't always get is the idea that the amount of energy it takes to vaporize a substance is the exact same amount of energy that's lost when something undergoes condensation. So the only difference is the sign. So if you're going this way, if you're vaporizing something, you're adding the energy, it's endothermic. If you're doing condensation on a liquid, it's going to be negative, but the amount of energy is exactly the same. Same thing with melting. The amount of heat of fusion for melting is that right there. Heat of freezing, you're going to lose that amount of energy right there. Notice they're the same. They're just going same amount of energy. They're just going different directions, thus different signs. Now, when we talked about vapor pressure before, how do we get vapor pressure? You put a liquid in a sealed container, and what happens is the liquid molecules slowly turn into gas particles. As that happens, some of the gas particles will slowly turn into liquid particles. So it's basically a two-way street. Eventually, they reach equilibrium. That's where the rates of both of them going from a liquid to a gas or a gas to a liquid are equal. And then we measure the pressure above the solution. So vapor pressure is a measurement. But the more gas particles you have above means the less intermolecular forces you have. So thus, if you have very low intermolecular forces, you will have a high vapor pressure. So when we talk about vapor pressure and intermolecular forces, that's how they get it. They put it in a sealed container, they wait till it reaches equilibrium, and they measure the vapor pressure. So vapor pressure is really a good indication of how easily something goes from a liquid to a gas, really, because what we do is we measure the gas above a liquid, and that's how we get the vapor pressure. Now, when we talk about gas liquid equilibrium, when it reaches, the first thing that happens is if you take a liquid, the molecules inside, some of them will have enough kinetic energy to escape the liquid. So then what happens, that's the vaporization phase. But then you also have molecules going back into the liquid through condensation. Eventually, the vaporization rate and the condensation rate will be equal to each other, and then that's where you have your basic vapor pressure. You count the molecules, or the molecules provide a certain pressure, which equals vapor pressure. Now, one of the key things for this section is you have to be able to read the graphs. A vapor pressure graph lists the vapor pressure, usually in torr, for some reason, on the y-axis, and temperature on the x. And what it is if you notice, as you increase temperature, you increase vapor pressure, because what happens is the more kinetic energy the molecules have, the easier it is for them to break free, thus vapor pressure increases. So temperature and vapor pressure are directly related. So as you notice, if I start here with ether, actually I'll start water. Water at 40 degrees Celsius, the vapor pressure is right around there. If I increase the water by 20 degrees Celsius, what happens is my vapor pressure increases, and it comes out, it's about right there, a little bit under 200. So when we read this graph, one key thing we can tell from the graph is the amount of intermolecular forces something has. Because when we get right here to 760 torr, 760 torr is 1 atmosphere, or what we call normal. Whenever we refer to normal on these graphs, normal boiling point is going to be 1 atmosphere or 760 torr. So the normal boiling point of diethyl ether is 34.6. The normal boiling point of alcohol is 78.3. And the normal boiling point of water is 100 degrees Celsius. So one thing we can infer from this graph is who has stronger intermolecular forces. Because remember, boiling point, the higher the boiling point, the higher the intermolecular forces. Hence, this has the lowest IMF. So this is a little lower. This is a higher boiling point, so this is greater IMF. And then finally, water right here boils at 100 degrees Celsius. It has a higher IMF than any of those three. If you look here, you have ethylene glycol down here, which must have much greater intermolecular forces. So a couple things you need to be able to do is realize that as you increase temperature, notice the general trend is the direct relationship between temperature and vapor pressure, which makes sense, because the more kinetic energy something has, the easier it can go from a liquid to a gas, that phase change. And then normal, you read across here. Normal boiling point is the temperature at which liquid will boil under 1 atmosphere pressure. We talked about that. So boiling happens when the atmospheric pressure and the vapor pressure are equal to each other, because normally atmospheric pressure can hold or push the molecules in a liquid, hold them down. Once they have the exact same vapor pressure, they can't be held back anymore, so they freely convert from a liquid to a gas. So you definitely need to know that definition and be aware of it. Boiling is when the atmospheric pressure and vapor pressure are equal to each other. If you look here, normal boiling points, you can find the temperature by just basically finding the normal value, in this case 760, till you hit the line, you drop it down, and you can read off. That's how you get the normal boiling points from a vapor pressure curve. It's just graph reading is really what it is. Heating curve is very important. When you look at a heating curve, this is I showed you in the first slide the SLG for figuring out solid, liquid, and gas. When you look at a heating curve, you need to know this region represents a solid, liquid, gas. Key thing to remember, which they focus on a lot on the AP exam, is in between. These represent the flat areas, represent phase changes. So this is where all the energy, the temperature of the substance isn't changing. That's why it's flat. What's happening is all the energy is going into basically separating the molecules. In this case, when it says solid and liquid are equilibrium, as you go this direction on a heating curve, all the energy is separating the solid particles and making them into a liquid, so they're a little closer together. Once you reach between point A and point B, that is basically melting. If you were going the other direction, it would represent freezing. That would be cooling though. And then if you look here, you're just heating the liquid. Between C and D, what's happening is you're going from a liquid to a gas. So you have a phase change. Once you reach point D, as you add basically, as temperature increases, as basically your time, or you're heating it, actually it should say heating time down here as you're adding heat, what happens is the temperature of the vapor will increase. So this is a graphical representation of basically SLG, going from a solid to a liquid to a gas. The key thing is representing the flat areas, understanding that they represent phase changes, and knowing what those phase changes are. You're just basically converting the SLG without sublimation and deposition. Those, the flat areas, represent the double arrows that you see here. If you look here, here's another example of, this is a heating curve for water. So you're adding heat as you go this direction. You have ice up till 0 degrees Celsius, that's where it melts. So then you basically have ice and liquid. You have the water melting as you go this direction. Then you're heating up the liquid water to 100 degrees. That's going to be its boiling point. And you're going to go from a liquid to a gas. And if you heat it even further, you end up heating the water vapor. Steam is what you get. So that's key, is to remember the flat areas represent phase changes. Another key thing to recognize is, remember we talked about the heat of fusion. That represents the amount of heat of fusion. That represents the heat of vaporization. It takes much more energy to vaporize, to separate the molecules completely, than it does just to melt them when they're still close to each other. The last thing is, you saw this last year, is phase diagrams. Another example of taking the SLG format is solid, liquid, gas. This is a representation of not just temperature, but temperature and pressure work together, because pressure can sometimes hold things together, can prevent them from separating, atmospheric pressure. So what we have here is, this represents the solid. Any region in here would be a solid, liquid would be here, gas would be here. These are called the equilibrium lines, because this represents the border as you cross over. That would represent melting. This would represent vaporization or boiling. And then if you go this direction, that would represent freezing. So if you look right here, this is where it's labeled. So going from a solid to a liquid, melting. Going the other way is freezing. Vaporization is liquid to a gas. Condensation is going to be going the other way. Sublimation and deposition are below this kind of Y-looking thing, or below here. So you have sublimation and deposition. Key other points are triple point. Triple point is a key part where in temperature and pressure, where all three states of matter actually coexist. So you can have a liquid, solid, and a gas in a flask at one point. Got to be aware of that. The other key thing on the graph is what's called the critical point. The critical point is there is a certain temperature at which, no matter how you increase the pressure, only gases exist. So a critical point is, beyond this point here, is the only thing that's going to exist is gases. It's basically what you're going to have. Last key thing is, here you have a phase diagram of, this is water, this is carbon dioxide. When you look at a phase diagram, you know you got a solid, liquid, and a gas, solid, liquid, and a gas. Most substances except water are going to be more dense as a solid than a liquid. How do you tell if something's not as dense as a solid as a liquid? Is this line right here. The line between the solid and the liquid. If that line has a negative slope to it, basically, if you imagine a clock, this is how I always think of it. Imagine a clock, 12 noon. In order for the solid to be more dense than the liquid, which basically every substance is, the way it works is this line has to be past 12 o'clock. If the line is before 12 o'clock, that means the solid is more dense, or the liquid is more dense than the solid. And the only thing that we know of that fits that description, if it's not made up, is going to be water. So I know at this case, water is actually more dense as a liquid than a solid. That's due to hydrogen bonding. And then you can read off different points on a phase diagram. It's graph reading. Remember, when they say normal, they're referring to 1 atmosphere. So if I trace this over, that line represents going from a solid to a liquid. That would be my melting point. Going from a liquid to a gas, that would be my normal boiling point. I could trace through here, drop down, and get my temperatures. So that's an easy way to read it. Here's 1 atmosphere right here. That would be my normal, in this case, sublimation point, because this represents going from a solid here to a gas. That's going to be sublimation since it's below the triple point. So this is basically graph reading. You have to be really aware of reading the graphs, reading the values off them, and finding the values. It's not a big deal. You just have to really kind of read and think about what you're doing. Have a great rest of your weekend. I will see you tomorrow. Hope you had a great Thanksgiving.